Paramanand Ashok Pawar, working as an assistant professor in electrical engineering department, NB Navle Sinhagad College of Engineering, Solapur. I have completed my BE from Government College of Engineering, Jalgaon, and MTech from TIT Bhopal in specialization power system. Now I am having the teaching experience of 8 years. Today we are solving one university problem on magnetic motive force method. Sometimes this method is called as Ampere turn method. So we'll solve the problem. So the open circuit and short circuit test reading for 3 phase star connected 1000 kVA 2000 volt 50 hertz synchronous generator are the field current value, that is 10, 20, 25, 30, 40 and 50 ampere. The open circuit terminal voltage, that is 800, 1500, 1760, 2000, 2350, 2600. The short circuit armature current, that is dash 200, 250, 300 dash dash. The armature effective resistance is 0.2 ohm per phase. Draw the characteristic curves and estimate the full load percentage regulation at 0.8 lagging power factor and 0.8 leading power factor. So this is the data available with us. Keep in mind, while we are solving the method, that is EMF method, there is only two characteristics are there, that is open circuit characteristics and short circuit characteristics. But while the solving the problem of MMF method, there is given value of the field current. So consider or keep in mind, this type of problem is for the MMF method, that is for the Ampere turn method. So first step to solve this problem is that first of all convert these voltages, that is the open circuit voltage, that is 800, 1500, 1760, 2000, 2350, 2600 by the phase voltage. So converting that particular three phase voltage into a phase voltage, that is divided by root 3, and we get the value, that is 462. Second, that is 866, that is third 1016, fourth one 1155, fifth one that is 1987, and last one that is 1501. So these are the values of phase voltages for the different readings of that particular thing. So from that characteristics we want to draw one curve, that curve is called as open circuit test characteristics and short circuit test characteristics. So then convert the full load phase voltage by its phase value. So that is phase voltage, that is 2000, so divided by root 3, it will give you the value, that is 1155, because as we know that these vector diagrams all are concerned with the different phases value, not for a three phase. So that's why convert that voltage into a phase voltage. Okay, so we know the fundamental formula for the kVA rating is equal to root 3 into VL into IL. So we have the 1000 kVA, so it is 1000 into K, that's why another 30, that is 10000000 is equal to root 3 into the value of VL is available with us, that is line voltage 2000 into, from that particular equation we'll get the value of line current. So the value of line current is 288.7 ampere. So from that particular values of the line current, we want to find out the value of the IF1 and IF2. So the voltage per phase at full load at 0.8 power factor. So we have, that is voltage per phase value, so is equal to V plus IARA cos phi. So we have the power factor, that is 0.8. We know the value, that is phase voltage 1155. We have the value of the load current, that is current is 288.7 ampere, and we have the value of armature resistance with us, that is 0.2 ohm per phase. So substitute this value, we'll get voltage per phase at 0.8 power factor, and that value of voltage is 1200 volt. So it will be very useful value of the voltage. So after plotting the OCC and SCC characteristics from OC curve, it is found that the field current necessary to produce a voltage that is 1200 is 32 ampere, and from short circuit curve it is found that the field current necessary to produce the current that is 288.7, that is 29 ampere. So from this particular reading we want to find out the percentage full load regulation for a given problem. So first of all, consider the value of cos phi, that is 0.8. From that particular equation we'll get the value that is phi is equal to 36.52, that is lagging. So from figure we have to get the value of OA, that is 32 ampere. The value of OA is 29 and the value of AB is 32 and angle is 36.52. Why the angle is 36.52? Because we have the power factor, that is cos phi. So cos phi is equal to 0.8, that's why the phi is equal to 36.52, and it is a lagging power factor. So as we know that for a lagging power factor we are considering the value of theta, that is specially that is 90 plus theta. So 90 plus theta, that is 36.52, so it will get the value that is 126.52 with OA. So draw this the value of IF, because in that particular condition the IF1 value is 29, the IF2 value is 32. So for that particular thing we have calculated the value of IF, that is 54.6 ampere. So for that particular 54.6, so that changes this value or connect this value to the open circuit characteristics curve, it will give you the reading that is open circuit corresponding voltage to 40, that is 54.6 is 1555, that is 1555. So this is in terms of volt. So after calculating the value of that particular E, it will be easy to calculate the value of percentage regulation. Therefore to finding out the value of the percentage regulation, E minus V divided by V. So we have calculated the value of E, that is 1555, minus we have the value of V, that is per phase 1155 divided by 1155. It will give you the value of voltage regulation, that is 34.6%. So this is the value of a percentage full load regulation for 0.8 power factor lagging. So similarly we want to find out the value of that is full load percentage regulation at 0.8 leading power factor. So again the value of cos phi is 0.8. So from that we can calculate the value of 5. So phi value is 36.52, but consider it is for a leading. So as we know that for a leading, that is the value is 90 minus theta for leading power factor. So subtract the value of theta from that particular 90, will get the value of theta, that is 53.28. So from that particular thing we know the value of IF1, that is the value of IF1 is 32. We know the value of IF2, that is 29. So from that particular angle characteristics we can get the value, that is OB. OB is a value of IF and that value is 27.4 ampere. So the open circuit voltage corresponding to 27.4 of the field excitation is 1080. So we'll get the value of E. So it will be easy to find out the percentage regulation for that particular value. So we have the value of E, that is 1080 minus 1155 divided by 1155 into 100. It will give the percentage regulation in terms of negative value, that is minus 6.4% for a power factor, that is 0.8 leading. So this is the solution of the first problem. So for solving this problem we want to attach one graph paper, and from that particular graph paper we want to draw the characteristics of OCC and SCC and follow the procedure which is given in MMF method, that is Ampere turn method. That is, first procedure is to find out the value of V, that is per phase value, that will be available at a different power factor. So it is 1200. So from 1200 we'll calculate the value of IF1. So from the short circuit current, that is 288.7 ampere, will get the value that is 29 ampere of IF2. So from IF1 and IF2 we can give, it will be for a leading power factor or lagging power factor. So for the first case it will be for lagging power factor, so it will be addition. So the total angle is 126.52. so while considering this angle we can calculate the value of IF, where the IF is the ampere turn with considering the demagnetizing effect. So from the IF we can get the value of OCC voltage. That voltage is called as E, and this voltage value is 1555. So from 1555 this is the voltage generated, that is excitation generated. So this voltage minus the voltage per phase divided by the voltage per phase will give you the value of voltage regulation. Similarly, for second case, we want to draw for leading power factor. So for sake of that, we know the value of IF1, that is 32. We know the value of IF2, that is 29. But the angle is leading. So in concern with leading angle, we want to minus, that is 90 minus theta. So we have the value of theta, that is 36 point. So 90 minus 36 point 72, it will give you the value that is 53.28. So from that particular angle we can get the value of IF, that is ampere turn. So the value of IF is 27.4. so from that particular IF value, that characteristics is again slightly means increasing to the open circuit characteristics, so that will be give you the value that is 1080. So from that 1080 value is the value of E. So substitute this value into voltage regulation formula and we'll get the value that is percentage regulation, that is minus 6.4%. So for solving of this problem, for getting the value of IF1, IF2 and IF for leading case, for lagging case, we want to draw the graph of that particular problem. Okay, so we'll start the second problem of that particular MMF method. This will be asked in 2018 examination. So a three-phase 800 kVA 3300 volt 50 hertz alternator gave following results. Again, the results are field current, open circuit voltage, short circuit current. So we have the field current values, that is 50, 60, 70, 80, 90, 100, and open circuit voltage, that is 2560, 3000, 3300, 3600, 3800, 3960, and short circuit current we have the value that is 190 ampere. So the armature leakage reactance drop is 10% of resistance and resistance drop is 2% of the normal voltage. Determine the excitation at full load, that is 0.8 power factor lagging, by MMF method. So in that problem we want to calculate the value of excitation, not percentage regulation. So this will be the calculating the value of excitation, means E. We want to find out the value of E. So will the first step, convert that voltage into a phase voltage, that is the phase voltage value is 1478, 1732, 1905, 2080, 2195, 2287 for corresponding values of open circuit voltages. So the normal voltage is in the given problem, that is given 3300. So convert that voltage into a phase voltage, that is 1905 volt. So while considering in the given problem there is given the value of the drop, we can considering the drop. So first of all calculate the value of drop. So that is IRA drop 2% of voltages. So that is 2% of voltages, that is the 2% of voltages, that is 1905's 2% means 38.1 volt. So I-axis drop is, that is I-axis means the reactance drop is 10%. So the value of 1905's 10% value, that is 190.5 volts. So we have the power factor, that is 0.8. So calculate the value of sine 5, that is sine 5 is equal to 0.6. So from that particular thing we want to calculate the value of E at that particular value. So we have the formula for basically the power factor is lagging. So in that particular formula there is a sign considering, that is plus sign, because here is the lagging power factor. So the fundamental formula of E, that is square root of V cos phi plus IRA bracket square plus V sin phi plus IXS bracket square. We have the value of V, that is 1905. We have the value that is power factor 0.8. We know the value of IRA drop, that is 31.8 bracket square, plus we have the value of V sin phi, that is 1905 into 0.6 plus 190.5 whole bracket square. It will give you the value of E, that is 2068 volt. So the exciting current required to produce this voltage as from means open circuit characteristics is the value, that is 82 ampere. So follow the same method, draw OCC and SCC, and from OCC we'll get the value of E, that is 2068. So for that particular 2068 value, calculate the value of IF1. So the IF1 value is a 82 ampere. So we have the fundamental formula, that is KVA is equal to root 3 VLIL cos phi. So from that particular thing we'll get the value of line current, that is, so in given problem, that is 800 kVA, so that is 800 into 10 raised to 3 is equal to root 3 into 330 into IL. So from that particular thing we'll get the value of IL. So the value of IL is 140A, that is 140 amperes. As see from, so short circuit characteristics excitation current, so for 140 the value of IF2 is a 37 characteristics, that is 37 ampere, because this is the value of IF2 and IF2 is corresponding to the short circuit current, that is 140 ampere. So from that particular thing we have drawn the triangular method, that is triangle, that is OA is 82 ampere and the value of AB is 37 ampere by the reading. So this the basically in that particular case the power factor is lagging. So we know the fundamental formula for lagging power factor, that is 90 plus theta. So add that value of theta, that is 36 point of that particular thing, will get the value, that is 123 point something. So that will give you the value of the 5. So from that particular thing we want to find out the value of IF. So for sake of IF there is another method which is calculated, that is basically, as we know that if we know the law of parallelogram, so law of parallelogram is said that is if it is a law of parallelogram, so it will give you the value, that is a square plus b square plus 2ab cos theta. So substitute the value of that particular cos theta into that equation. So we'll get the value of OB. So the value of OB is near about 1.8 ampere. So substitute all the value of A, all the value of B, all the value of cos theta, because as we know that here is cos theta, that is 180 minus, that is 126, will give you the value, that is 53.8. So it will give you the value of OB, and this value of OB will give you, that is 1.8 ampere. This is one of the method. If you want to calculate by another method, by a regular practice, so the regular practice method is that if you know the value of IF1, if you know the value of IF2 with an angle, that is 90 plus theta, that is 126 or 123.6. So simple measurement, this is the value of OB, and we'll get the OB value is nothing but the IF value, and which has the value of excitation current. So from calculation we'll get the value of excitation current, and that excitation current is the value, that is 1.8 ampere for this problem. So this is the problem which is based on the MMF method of a alternator. So keep in mind, while solving of this problem we need to draw these open circuit and short circuit characteristics of a alternator on a graph paper, and from graph paper we'll get the value of IF1, IF2 and IF. Thank you. Thank you very